First of all, what is statistics? So we use statistics to gain information about a group of objects and or to make decisions and predictions when randomness is involved. Okay, so let's break down this sentence. So we want to gain information about the population. That makes sense, right? And we want to make decisions and predictions. And this is a very, very nice thing about statistics, because how can we define, I don't know, if a vaccine works, for example, or not? So probably we want to give the vaccine to some people and see if these people have better health outcomes than the people who didn't receive the vaccine. So if they do have better outcomes, then we can make decisions, to give permission to this vaccine to be on the market. And we also want to make predictions. For example, we want to see if the middle school grades can predict high school grades or future academic career. Now, can we collect all the people of the population, all the members of the population? Sometimes we can do, and this is called census here. So census is the collection of data from every member of population. Now, this is very, 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 very hard, especially if the population has too many members, right? So for example, if your population is the Dutch people, or the Dutch population, let's say, this is 17 million people. It's really, really hard to collect data from all of them. So most of the times, what do? We sample. We collect a sample. So because it's very, very difficult and very, very expensive and very, very, very time consuming to recruit all the members of a specific large population, we take some of those members. And we call this thing a sample. That makes sense. So how do we collect sample data? And there are 7 different methods. Let's go through all of them together. So the first and the easiest one is the voluntary response sample. So in that case, subjects decide themselves to be included in the sample. So you see a survey or a research or a study that asks for participants, and then you voluntarily say, hey, I want to take part in this study. I want to be the research rat. I mean, the participant. So this is the voluntary response sample. Now, next to that, we have 2 random samples. The first one is called random sample, and the second one is the simple random sample. So under the random sample, each member of the population has equal probability of being selected. And in simple random sample, you can see that each sample of size n has equal probability of being chosen. So the parts that says equal probability, it's exactly the same in both of these cases. And this has to do with random, the word random. So when a sample is random or simply random, that means that all of the things have equal probabilities of being selected or of being chosen. Now, what the difference between these 2 techniques is the things that have equal probabilities. So in the first case, in a random sample, it is the member of each population, it's each member of the population that has equal probability. On the other hand, under a simple random sample, we divide our population into smaller samples, each one with the same n, and then each of these samples have equal probability of being chosen. So here we talk about individuals, and here we talk about groups, let's say. Another systematic sampling. We rank all the members of the population. We have a starting point, And I don't know, every second or fifth or 10th member, select all of these people. There are three more techniques. Convenient sample, which is really easy. It gives us very easy and very available results. So let's say, I don't know, I'm running a study and I call my friends to take part in that, convenient sampling. And we also have two techniques that also look to each other, they look similar to each other, and they have to do with how you divide the population into smaller groups. So under stratified sampling, we divide the population into subgroups, we call them strata, and we do that based on some characteristics. And then we draw a random sample from each group. So let's say that we have a population, like the Dutch population, and we want to divide that into different strata. I don't know, based on, we can do gender, income, and if they live in big cities or in rural areas. And then you draw some people from each of the group. Now in cluster sampling, you divide the population into sections. Again, there are subgroups. In this case, we call them clusters. But now you don't select people from all of these groups. You just select some of these clusters, all of them. Does it make sense so far? All right, cool. If there's any question, let me know. All right, so we have two different methods when it comes to two different methods of studies, let's say, to big categories of studies. So on the one hand, we have observational studies. In this case, we just observe subjects, we observe the participants. We don't modify them, we don't change them. We do not have a treatment on them. And on the other hand, we have the experiments, where we actually try to change something in the participants. We try to modify them with some kind of a treatment. Now, I know that an experiment can be a very easy thing to think of. But what about observational study? Can you come up with an observational study? Can you give me an example of an observational study? A study in the hospital. How? Animal study. Ooh. Studying medicine and treatment. That will be an experiment, right? Observe how they react to medicine. But if we give them a medicine, that will change them, right? So it's not an observational study. If we observe something and give conclusion to it, like rats living or how people living. Yeah, this is actually an observational study. Yeah. So yeah, let's go back to the medicine thing. So if you give a medicine to some people, then you change them. Maybe, but that's the idea behind that, right? So give them a kind of treatment. You give something that will change their health, maybe the better side or the negative side. I mean, if you give something and it will turn bad to them, it will be very unethical. But anyways, so yeah, you can observe people. You can observe people. I mean, there are some studies that observe how people behave in schools, or how children with how do you call them, with severe disorders when it comes to personality or learning disorders, you see how they behave in the class. or you can also see how animals behave. Yeah, that's true. All right, so we also have three kinds of studies based on how or when the data is collected. So first we have the retrospective or the case control studies. Then here we have all the data from the past. We have the cross-sectional studies, and here we measure our data once. And we have the prospective, or at least in my field, we most call them longitudinal studies, where we collect the data many, many times. Now, when it comes to experiments, usually we have a control and a treatment group. So as we remember from the previous slide, when it comes to experiment, we try to change participants, right? We try to modify them. So we take our sample. In most of cases, we divide them into the control and the treatment group, and we try to modify the treatment group or the experimental group. And below that, you can see two nice phrases: single blind and double blind experiments. So can someone tell me what is a single blind experiment? When an experiment is single blind? The subject is unaware of what drug has been given, when the person tested doesn't know what that is tested. Perfect. So, congratulations. This has to do with participants, right? So the participants do not know in which group they are, either in control or treatment. They don't know if they took the placebo or the real treatment. They have no idea. So in single blind experiments, participants do not know. When it comes to double blind experiments, participants have no idea what's going on, but also the researcher has no idea if the participant belongs to the control or the treatment group. And there's another level of blindness. We call it third blind, but I don't think that this is part of your material. But just so you know, there's also the third blind experiments where the people who analyze the data have no idea what's going on. Yeah, so in experiments, we can also have the placebo effect or the experimental effect, different effects that we very hard to explain, but they can change our results, right? So the placebo effect is basically when you don't have any treatment, but you see some effects of the real treatment. So for example, you get nothing, or a pill that you think it's a medicine and it's actually, I don't know, sugar, and it can improve your health. Sugar improves your health. Amazing. Yeah, so single blind participants don't know, and double blind, the researchers also don't know. That's a difference. That's a difference. I mean, in the single blind, only the participants don't know. In double blind, the participants don't know and the researcher doesn't know. So for example, if you have a real vaccine and a placebo vaccine, in double blind experiment, the participant comes to the lab, he or she receives a vaccine. They don't know if it's the placebo vaccine or the real vaccine. And also the person who administrates the vaccine, who gives the vaccine to the participant, doesn't know if it's the real one or the placebo. Make sense? Perfect. All right, so let's now talk about the types of data, because we talk about the types of studies. So now we have either categorical or numerical data. So let's go from the left part of this picture. So under categorical data, we have the verbal labels or the verbal variables and the coded ones. So they're exactly the same thing. We now, since we talk about categorical data, we talk about categories. So for example, we can divide our sample based on which type of vehicle they use. And we can say that participant 1, 2, 3, they use a car, 5, 6, 7, they use a truck, and all the others, I don't know, they use an SUV. And then you can also code that with numbers. So you can define car as 1, truck as 2, SUV as 3, and stuff like that. Now, there are some variables that have many categories, like the vehicle type. Here we can add more types of vehicles. And there are some variables that only include 2 values. So we call them binary. I'm not quite sure if gender is one of them. I wouldn't say that. But let's, for the sake of the example, pretend that gender is a binary variable that includes 2 values. On the other hand, we have the numerical types of data. So we can have discrete or continuous types of numerical data. So the discrete is like numbers that don't have decimals. So you can see the broken eggs in a carton can be 1, 2, 3, and up to 12, for example. But when it comes to continuous data, you can have decimals. So the patient waiting time can be 14.27 minutes, for example. All right, that was not so important. This is really important. And I think there will be a question in your exam about that, because it's a really nice question. So we have, based on this graph, we can elaborate and we can have 4 different types of data, or you can say 4 different measurement levels, or 4 different types of variables. It's exactly the same thing. Most of the times we call them measurement levels. So the first one is the nominal. In this case, we have numbers, but these numbers refer just to some categories. For example, I can assign a number to all of us here in this class based on which countries we came from. So for example, I come from Greece. I can have the number 1, for example. People who come from the Netherlands will have the number 2. No, but people who come from France, they have the value of 3. People who come from Germany, they have the value of 4. Now, we have 1, 2, 3, 4, but these numbers just refer just to some categories, nothing else. We cannot add them. We cannot say that 1 is better than 2. We cannot do that. So this is the nominal level. Numbers that are referring to categories and nothing else. Then we have the ordinal. So here we have again numbers, but now we order the categories. So we can have rankings. In most of cases, when you see a ranking, it will be an ordinal variable. For example, I don't know if you have seen Eurovision Song Contest before, but at the end, all the countries have some points, and they're ranking based on these points. So you still have, I don't know, like Netherlands number 1, Israel number 2, Spain number 3, Portugal number 4. So in this case, still we refer to categories, but there is an order. So if Netherlands is number 1, that means that it is better than number 2 or better than number 3. So this is the ordinal type of variables, or the ordinal measurement level. And now we have the interval and the ratio. So as you can see, they both refer to proportional differences between data, but in what makes them different from each other is how they handle 0. So in interval variables, the 0 is totally arbitrary. We woke up in the morning and we said, oh, for this thing, the 0 means this thing. For example, temperature, right? So we measure the temperature in Celsius, degrees, here in Europe. So what is 0 Celsius degrees? It is a little bit colder than +1 Celsius degrees, and a little bit hotter than -1 Celsius degrees. But 0 doesn't mean that we don't have any temperature. It's just like there is a temperature outside, and we woke up in the morning and we said, this is 0 Celsius degrees. I don't know who thought about that, but that's it. The 0 here is totally arbitrary. But when the 0 is absolute, when the 0 means that we don't have any of the variable that we measure, then it's a ratio. So for example, age is a ratio variable. Why? Because if you have 0 age, that means that you don't have any age at all. So for example, awesomeness, if we measure how awesome a person is, can be a ratio variable, because if you have 0, that means that you have no awesomeness at all. It's a ratio variable. Any questions here? Cool. So let's practice with that. What kind of oh, there's something in the chat. Okay, perfect. So what kind of data types are these examples here? So let's first talk about weight. What kind of data type is weight? Ratio, continuous, true. But when it comes to nominal, ordinal, interval, and ratio? So we have one interval. And a very brave person who said interval. All right, so the truth is it is ratio. And why? Because again, the difference between the interval and the ratio comes to how 0 is defined. So if you have, what's our variable? Weight? Yes, you have weight. That means that you do not have any, if you have 0 weight, that means you do not have any weight at all. So that means it's a ratio variable. In the interval variables, the 0 doesn't mean that you do not have any of this variable. It's just another value of this variable. Just like 0 degrees Celsius is a value of the variable temperature. It doesn't mean that you do not have any temperature at all. So yeah, weight is ratio. Gender is what type? Some people say nominal. Okay, we have established the norm here, the social norm here to say nominal. Yes, it is true. Gender is nominal. What about the grade for an exam? Okay, so basically you have a grade from 0 to 10, for example. Do you think it's an ordinal or a ratio? So some people saying ordinal, some people saying ratio. Ordinal. Interval. Absolute zero is always 0, 0. Yeah. I mean, absolute zero means that when you have 0, you don't have any of the variables that you measure. Okay, some people say it's ordinal, some people say it's ratio. There's one person who said the interval. That's nice. I would say it's ratio, to be honest. Because you don't, I don't know if you ratio because 0 means you failed. Yeah, I mean, you can also fail with 1 or 2, for example, based on the criteria of the exam, based on the rules of the exam. But how can you distinguish between these things? So here under nominal, for example, we have this picture here, very low quality picture, but okay. So under nominal variables, you can see that attributes are only name, okay, whatever. In ordinal variable, there's one step above, so now attributes can be ordered. In interval, we have one step above, distance is meaningful. In the ratio, we have one step above, absolute zero. So that means that the types, the measurement levels carry on with the attributes of the previous ones. So even though ordinal variables describe attributes that can be ordered, it's the same for interval, and it's also the same for ratio. This attribute here, this characteristic of the ordinal variables, continues on the measurement levels that is above them, that are above them. So ratio variables can also describe attributes that can be ordered, but with a difference that we have an absolute zero. So a zero, that means here we have a grade for an exam. So 0 means you don't have a grade. I mean, you did everything wrong. And when it comes to ranking in a sport game or sports game, what type of measurement level is this? What letter grades? A plus, A, B ordinal. Oh. Hmm. Yes, I don't have any experience with these types of grading, but so there is A plus, then A and A minus. I don't know if you can, then there's B plus, and yeah. So if you add add these values and they make meaningful result, then it's at least an interval type of measurement level. So for example, if you say someone took a plus minus a, what's the result of that? F? I don't think so. I don't think that you can make mathematical additions or multiplication. I don't think you can make any multiplication with letters. I don't think you can also do additions. So I would say it's ordinal if you have a plus, a minus. Google says it's ordinal. This is about the letter grades or the ranking in a sports game. Yes, yes, letter grades. Yeah, I think so. Yeah. All right. What about ranking in a sports game? What type of measurement level is the ranking in the sports game? Ordinal. Yeah, it is ordinal. Yeah, true. So all the rankings are ordinal. So if you have a question about rankings, it would be amazing. The gender is nominal. The gender is nominal. Yeah. All right. So any questions here? Do you feel very confident about distinguishing between nominal, ordinal, interval, and ratio? No, perfect. Joanna, what's the tricky part here?
I just don't get it. I'm sorry.
Is this something that really how to say it's really unclear, or everything is unclear here?
Just the ratio, maybe.
Oh, just the ratio. Okay. So maybe the distinguish between interval and ratio.
Yes, exactly. Thank you.
No. Okay. Perfect. Okay. So interval and ratio. So here we have numbers, right? I mean, in all the cases we have numbers. But the difference between the interval and the ratio is that the zero. Okay, so the proportional difference between data is exactly the same thing. So if you have, I don't know, age of 27 and age of 15, you see there's a difference of 12 years. That means something. But it's also the same with interval variables. You can have 20 degrees Celsius and you can have 10 degrees Celsius. It's still 10 difference of degrees. That also tells you something. So this part is exactly the same in these cases. We both have proportional difference between data. The only thing that distinguishes them is the zero. So in interval variables, the zero is arbitrary. And I can only think about temperature as a good example. So I'm going to say that once again. So 0 degrees of Celsius is a value of temperature. It doesn't mean that you don't have a temperature at all. But in ratio variables, if you have 0, that means that you don't have any. So if you have 0 weights, that means that you do not have any weight at all. If you have 0 weight, that means you don't have any weight at all. If you have zero income, you don't have any income at all. But in temperature, it's not the same. If you have zero temperature, you have a temperature out there. Okay, great.
Thank you very much. Thanks.
No worries. All right. So let's now discuss about the graphs. So the first one is the bar chart. So the bar chart is usually for categories or for quantitative data. So what we see here is on the y-axis the frequency, and here is how frequent its grade is. Now, on the left part, on the left bar chart, you see two W's here, let's say, but on the right one, it's more like the signal that we have in our phones. If I tell you that this is exactly the same data sample, why this bar chart looks like that and why this bar chart looks like that? Additive, perfect. R, thank you. So here you have the cumulative frequency, right? So here we have the frequency of 5, and this is the frequency of 6, and this is the frequency of 7, and blah, blah, blah. But now here we add. So here we begin with a frequency of 5, it's 2, just like here. And then we add 6, then we add the 7 on top of that. On top of that, we add the frequency of 8, blah, blah, blah. So when we are at the end, we have 100%. So basically, the take-home message here is that the bar chart is usually for categories. Now, we also have another thing that's very similar to bar chart because we still have bars, but we call it Pareto chart. And here we usually have, it's again the frequency or the value of some categories, but this this also includes an ordering. So you can see that we start from the country or the region, let's say, that has the highest population, then we go with the second one, we go with the third one, the fourth, the fifth, and stuff like that. So it's not like the bar chart here, which is ranking based on the X values. Here it's based on the Y values. And it's more for a nominal level of measurements, right? So you can see that this is nominal because if I say China is 1, India is 2, Africa is 3, South America, this is 4, US is 5, and blah, blah, blah. It's just numbers that signify which category it is. It's not like China is number 1, it's better than India, which is number 2. And now it's here is exactly the same data, but with a pie chart. So if a variable has a big value, it has the biggest part in the pie, let's say. So the China here has the biggest one. India has also a big one. Africa was the third one, right? It was, oh, here it is. So again, we have frequencies, but now in another types of visualization. And we use that mostly for qualitative data. And now we have the bar chart, but for interval variables and ratio variables. So when something is good for interval, that also means that it's also good for ratio, right? Because as we said, when there is an attribute or a characteristic of an interval variable, it's also of the ratio because it's one step above. So the histogram is the bar chart, but Here we also measure frequency, just like before we did with bar charts. But now, instead of categories, instead of categories, we now have interval variables or ratio variables. So they're continuous, as you can see. And the area of bar, so the area of the bar is proportional to the frequency. So how frequent is the values at the x-axis. So the proportional to the frequency in interval below the bar. Below the bar, what is that? The x-axis. All right, and there's also the time series plot. So we have a graphical representation of quantity that varies over time. So here, for example, we have the number of sunspots. I have no idea what a sunspot is, but this, you can see how these numbers of sunspots change based on time. And I have a very weird question. Can you think of a scientific field that really uses time series plots? Sleep phases. Okay. Electrical activity in brain. Whoa. Performance through years. Marine biology, environmental science. Oh, okay. That's nice. It's really, really nice. Also, you came up with these things very quickly. Nice. Yeah, usually in time series plots, you have many years. So I don't know if sleep is one of them, but I guess you can also have a time series plot with sleep. Why not? It's 8 hours. For me, it's a lot. World population. Oh, changes based on the years. Amazing. Yeah, true. And also came up. I have an aunt. My aunt is an archaeologist, and recently her research team published an article, and I just saw it and I just copied the time series plot. So here it's a time series with many years, and it's the sea level. It's the sea level in some areas of Greece, the Aegean island chain. So archaeology can be one of them, or I said marine biology. Wow, I didn't know that it was a field. All right, cool. Any questions about the graphs? All right, cool. So we're going to talk a lot about histograms and the box plots also in a moment. All right. So we talked about what kind of studies we can do. We talked about how we measure the variables that we measure with ordinal, nominal, interval, and ratio. We talked about how to make graphical representations of this data with different graphs. Now, but let's now interpret more these distributions, these graphs. So why do we do graphs? Because we want to see a visual representation of the data. And what we can definitely see in these visual representations is a distribution of the data. So how do we describe the distributions of the data? We talk about 4 different things. Let's go through all of them. First, let's talk about shape. So we can have 3 plus 1, let's say, different shapes. So the first one is symmetrical. As you can see, it's like a normal distribution. So it's like a bell. It's really nice. We like that. So you can see here, for example, the mean is 0, and you can see that almost do have few values on the negative side, we have few values on the positive side, and most of them are close to the mean, close to the center. We have the right skewed distribution, which looks like this. So we have a peak very early or very left, let's say, so on the negative values or of the smaller values, right? And we have the tail over here. That's why we call it right skewed, because the tail is on the right. So please remember that. We don't care about the position. I mean, we also care about the position of the peak, but in right skewed, the peak is on the left part of the graph, and the tail is on the right part. Now, it's the other way around with a left skewed distribution. So a left skewed distribution would look like this. So it will have a tail on the left and the peak on the right. And the third one is the uniform shape. So uniform shape, it's just like most, like all the values have about the same frequency, they're about the same distribution. So a single line can describe very well. This is the uniform. It's really, really hard to get a uniform, at least in psychology. I don't know about other fields. That was the shape. So symmetrical, right skewed with the tail on the right, left skewed with the tail on the left, and uniform. What tail of uniform has the uniform? What kind of tail has the uniform one? It doesn't have a tail. It's a single line, this purple line here. All right, so first we talk about shape. Now let's talk about location. So here you can see exactly the same graph. See, it's exactly the same, but what changes is the location. So here, everything is around 0. And you see each step is has to do with 1. So here we have 1, we have 2, we have 3, -1, -2, -3. And here we have all the values around 10 with the steps again with 1. So 10, 11, 12, 13, 9, 8, 7. So here it's around 10, it's here around 0. So the values of the x-axis matter. All right, that was the location. And now let's talk about dispersion or variation. It's another word to say exactly the same thing. So here we have exactly the same x-axis. As you can see, it's 0, -5, -15. I don't know why -10 here is missing. So we have around 0 and steps of 5 in its case. But here you can see that all of my data are very close to each other, right? So you have 0, but the most negative value is -4, 3, I don't know. And the positive value is +3, 4. And it's very, it doesn't have, huge variation. It's very close to the center, close to my location, to 0. But this thing here, it's not the same. So even though we have exactly the same x-axis, you can see that the graph is very spread, has a large dispersion. So we have values that range from -14, maybe, to higher than +15. So this is the dispersion or the spread. Most of the times I call it spread. And this is the last thing, it's the skewness. That this only is applied to the skewness, to the skewed distributions, right? So that is not applied to symmetrical or uniform. So if you have a skewed distribution, you can also talk about the skewness here. So let's make a recap question here. So we have a distribution here that has the peak here and the tail here. And we have another distribution here with the tail here and the peak here. Okay. So this distribution, is it right skewed or left skewed? Right, right, right. Yeah, it is right skewed. Why? Because the peak is on the left and the tail is on the right. So this is a right skewed distribution. On the other hand, yeah, perfect. On the other hand, the left skewed distribution has a tail on the left and the peak on the right. Now, you can also call the right skewed distribution here positively skewed distribution. Why? Because again, the tail is on positive numbers. So it's more to the right. So on the right, it's the positive numbers. That's why we call this positively skewed distribution. So the tail is on the right, the tail is on the positive numbers, so it's a right skewed distribution. It's a positively skewed distribution. On the other hand, in this distribution, the tail is on the left, the tail is on negative numbers, right? Because on the left, we have the negative numbers, so it's a negatively skewed distribution. All right, so you can also remember this part here, or in this part. An easy way to remember them is first, find the mode. So the mode is always at the peak, at the highest point of the peak of the distribution. Why? Because the mode is the number that appears the most, right? It's the most frequent number, the most frequent value. So it's always at the highest peak of the distribution, highest point of the peak. So this is the mode here, and this is the mode here. So the median is always at the middle, and then you have the mean, right? So in positively skewed distribution, the mode is less than the median, which is less than the mean, right? Because these are more on the right, and on the right we have positive numbers, which are higher numbers. So the mode here is smaller than the median, it's smaller than the mean. It's the other way around with the negatively skewed distribution. The mean is lower than the median, which is lower than the mode. Does it make sense? All right, I think it's 11 o'clock. So we can have a break of 5 minutes and we can come back at 11:05. Yes, are. The median, the mean, and the mode is exactly the same when the distribution is normal. Yes. If it's perfectly normal distributed, then it's exactly the same value. when can we say that the distribution is normal or when not? Oh, okay, cool. The normal distribution looks like this. So it's a symmetrical distribution, right? So if the line goes like that, you can tell it is. I mean, in your exam, it will be very clear if it's a normal distribution or not, based on a graph. In real life situations, you have tests that do that. They test if the normal distribution exists in your data or not. I think one of them is called Kolmogorov-Smirnov, and the other one is Shapiro-Wilk test. Shapiro-Wilk, oh my God, names. The most difficult thing. Okay, so the symmetrical isn't, yes, symmetrical shape is a normal distribution. Yes, it looks like that. It's a bell. No worries. All right. So we talked before with about the means and the medians and the modes. So let me refresh your memory. The mean, I think we all know how to find means, right? So we symbolize that with X bar in our sample. Okay, so let me first tell you that all of these are sample measures. So these measures refer to samples, not the population. It's a sample that we do the statistics to. So the mean, which is the X bar, of course, we add all our values, and then we divide by the number of these values. The median, or the median is the number, the value that breaks the sample into two parts. So the value that divides my sample into different exactly the same equal parts. So it's the 50th value, let's say. If you have 100 values, it will be the 50th. Would be? Yes, if you have 3 values, for example, it will be the second one, because then you have one below and one above. So how do you find that? It's based on the number of the sample that you have. So if this number is an odd number, you do this beautiful formula. That's very simple. N plus 1 divides by 2. So let's say that you have 9 values. So it's 9 plus 1, 10, divided by 2, 5. So you take the X, the value of the participant number 5. And then you find the median of your sample. And if your sample size is even, then you do this beautiful formula here. So it's the half of the participant, let's say it's 10. We have 10 participants, right? So Rn is 10. It's the half of the X of 10 divided by 2, that's 5, right? Plus 10 divided by, that's not correct. It's 2 plus, plus 1, I think. It should be outside of the parentheses. So it's the one that's between participant number 5 and participant number 6. I don't know, this is correct. Yeah, oh my God, this is high school math. Yes, so it's 10 divided by 2 first, which is 5, plus 1, 6. Yeah, makes sense. So the median is between the X of participant number 5 and the X of participant number 6. So for example, if you have 8 of 10 people and you want to find the median, it will be the half of the half. The mean, let's say, of the age of participant number 5 and the participant number 6. The mode is the most occurring data value, of course, if there's any, because you can have, let's say that you measure the age of 10 different people. All these 10 people can have 10 different values. So in that case, you don't have, well, you can say that you have 10 different modes at the same time. But let's say that you have 2 people that have exactly the same age, and all of them have different values, and the rest of them have different values. So then you have a bimodal, because you have, oh no, it's not this. If you have like 2 people that have exactly the same age and 2 other people that have exactly the same age, and then 6 different values, then you have a bimodal, because 2 values appear twice, appear most of the times. And if you have many different modes, we call it multimodal. So more than 2. Does it make sense here? Yeah. Okay, cool. Any questions? Cool. So let's practice. The sample mean and the sample mode are always equal for data at the ordinal level of measurement. Is it true or not? Have one no. Have one I don't know. Okay, another no. Okay, cool. The truth is, oh, yep, why are we there? Cool. So the truth is that it's not correct. And let's find an example with ordinal variables. Let's say that we have gender, for example. So we have 1 as female, 2 as male. I'm going to say 3 as non-binary. Okay, so 1 female, 2 male, 3 female, non-binary. So the mode here would be 2, right? Yes, the mode here would be 2. But what happens if I find the mean? So it will be 1 plus 2 plus 3 divided by 3, right? In that case, it's also 2. But what if I say that females are 1, males are 2, and non-binary is 10? Can I do that? I can do that because I don't have ranking under ordinal variables. So I can put whatever values I want. So then you have females 1. Let's try to find the mean. The mode it's exactly the same. And the mean now it's 1 plus 2 plus 10, which is 13 divided by 3. That's 4 point something. In that case, my sample mean is not the same as my sample mode. So, no. And also, at ordinal level of measurement, we don't find the sample mean. It doesn't have any value to give us. We just have categories that we just give numbers. What's the sample mean? We don't want the sample mean. It doesn't say anything to us. What's the sample mean of gender? Doesn't give anything. it's a little bit stupid to calculate the sample mean for the ordinal value. Okay, so we talk about the central position with the mean, the mode, and the median, but you also have the measures of variation in our sample. Okay, so again, we talk about sample measures here. So we have the variance, the standard deviation, and the range. So the variance, S squared, and the standard deviation is a square root of sample variance. So both of these things here, both of these measures, they give us an indication of how much the values deviate from the sample mean. Okay, you remember the histogram that were like that? So we can calculate the standard deviation or the variance, and that can give us how much the values deviate from the mean or the mean. And this is also really nice way to calculate. So for all the people that you have, first of all, you find, for all the participants that you have, first of all, you find the mean of your sample. And then for each participant, you take out his or her value minus the mean, and this you square it, and it's divided by n minus 1. With a histogram example, okay, yeah. So let me also discuss the range, and I will come back to it. So the range is very easy. It's the maximum and the minimum, right? So the range is between the maximum value and the minimum value. So let's try to see all of these three measures in the histogram here. Of course, we cannot calculate it. Let's first discuss the range. So in this, on the left histogram, we have a smaller variation, we have a small dispersion. So it goes from, how do you say this? It will be -4, let's say, to +4. So my range is between -4 and +4. But here it will be -15 almost to +16, let's say. But this has to do with the range, because the range is between the smaller, the minimum value, and the maximum value. So let's say that you have two different samples, and you can already just give the range, and it will give you an indication of how the values distribute around the mean, right? So here you have a smaller range, so a smaller dispersion. Here you have a larger range, a larger dispersion. And this also, if we had the values here, we could also calculate the standard deviation and the variance. And this will also give us the same picture. So here, the variance would be very small, and the standard deviation would be very small. And here, the standard deviation and the variance would be very big. Why? Because here we have a larger dispersion, a larger spread. And here we have a smaller spread. Does it make sense? Perfect. Perfect. Cool. So, three different measures of variation of spread. Now, we talked before that all the things that we discussed so far are sample measures. So they are the measures that have to do with our sample. And this is what we try to do here, right? We talk about, we have a population, we take a sample of n items, of n participants. Why? Because we cannot take all the members of the population. So you just take a sample. and you estimate, here's the mean of the population. You estimate the mean of the sample, you estimate the variance of the sample, and the p-value of your test. And then you try to make an inference based on these numbers about the population. So you try to generalize the results that you have, the conclusions that you have, to the population. This is what we call inference. So we just call those things inferential statistics. Now, an easy way to remember that is that when you see Greek letter, this has to do with the population. If you see an English letter, this has to do with the sample. And the formulas are exactly the same thing. They don't change at all. But here, for example, let's say the variance, instead of the mean that you have from the sample, you have the M, which is the mean for the population. All right, so let's discuss a very, very important part now, box plots. So again, we talk about the distribution of our data, right? So we have the data, we distribute them, and we have this beautiful box plot that ranges from the minimum to the max value. So the first line here, the first green line here, and the last green line here refers to the minimum and maximum values. Then we also have a whisker, so this line here and another one here. But let's talk about the left part. So we have the minimum, a whisker, and then we have another vertical line. Is it vertical? Yeah, right. These are verticals or horizontal. Anyway, this blue line here. So this blue line refers to the lower quartile, or Q1. This is the value of the 25th percentile. So if we divide our sample into 4 different percentiles, in 5 different percentiles, so this is the minimum, this is the 0 percentile, this is the 25th percentile. So this is the value of a person of the 1/4 of my sample size. Let's say that you have 100 participants, right? This will be the value of the number 25th. Then we have another box. You have the median here. So the person that divides the value that divides the sample into 2 equal parts. This is the line inside the box, and the line that closes the box, it's the Q3, or the upper quartile, the person at the 75th percentile. So again, if you have 100 participants, this will be the value of the person at the position 75. And then you have another whisker, and then you have a max. Oops. Yeah, this from the Q1 to Q3, all of this part here, all of this box, we call it the interquartile range. So IQR is the range between participant number 25 and participant 75. Again, if you have 100 participants. But a box plot can also include some outliers. Here, let's say. So these are the participants. These are the observations that lay outside of the whiskers. And why do they lay outside of the whiskers? Because they differ significantly from the other data. So these are 2 extreme values. In this case, they are positive values, right? Because they're higher than the max. So there are two extreme positive values. Okay, any questions here? Can you give it with student grades? Oh, okay. So I cannot give you with student grade because I don't think that will be an outlier of that, but I can give you with IQ. So for example, okay, yeah, sure. So let's say that you have measured the IQ of lots of people. So here you have the minimum value. Here you have the maximum value. So the person with a lower IQ, and the person with a higher IQ. And then here the Q1 will be the value of the person who is on 25th percentile. This is the median. So this is the person who divides the sample into two similar groups. Q3 is the 75th percent. So you can also have, when it comes to outliers, this will be, I don't know, people that score extremely high or extremely low on your IQ score. So this is the most, I think, the most important thing to remember when it comes to outliers. Are extremely values, extreme values, that differ significantly from the other distribution. Now, you can also observe the box plot and say some things about the distribution of your data. So for example, here, what can I see? Also, it's on the right, it's not on the top, but okay. What can I see? Yeah. Yeah, so you can translate the box plot into histogram. Yeah, true. How do you do that? Okay, so let's say if there's a normal distribution, this box plot looks like a normal distributed. Why? Because here we have the minimum, then we have a whisker that's exactly the same. I can say that they're exactly the same. Yeah. They look like that. We have a Q1 at some point, and then the distance between the Q1 and the median is very close to the distance between the median and the Q3. You see that? So we have a box, and the median is about at the center of it. Now, if your two whiskers have the same, about the same length, and the median is at the middle of your box, then you have a normally distributed data. Have a normal distribution variable. If the median is closer to Q1, that means that you have the median is more on the left. So that means that you have a positively skewed distribution, right? Yeah, the middle is more on the left. So you have a positively skewed distribution. When the median is closer to the Q3, then you have a more negatively skewed distribution. I think we're going to see an example in a practice question. So let's wait for it. Hope this will become more clear. All right, so let's go through all these exercises. Number A, the mean is strongly affected by extreme values. Yes or no? Yeah, perfect. I think it's clear to everyone. The mean is affected by the extreme values, either positive or negative. That's true. Number B, in a systematic sampling, we simply use results that are very, very easy to get. Is it true or not? False. Why is it false? Can you also give me a reason why? Yeah, that's convenience sample. Yeah. Do you remember what we were doing in systematic sampling? Okay, so in the systematic sampling, I think this is stratified, if I remember correctly. I think in systematic sampling, you rank the participants, then you begin with someone, and then you take every case, right? Like every second or every fourth, every fifth, yeah, every case, yeah. This is systematic sampling, yeah. Nice try, nice try. Okay, so a bar chart can be used to visualize data at the ratio level of measurement. Is it true or not, and why? By the way, I'm going to share the solutions later. Yeah, don't worry about that. Okay, so Alexandra says yes, because they're meant for quantitative data. Any other idea? Okay, so I would say that histogram is more appropriate, to be honest, because the histogram is really, really good for interval and ratio variables. So I would prefer to do histogram, to be honest. And download speeds in megabps per second. Are these an interval level of measurement or not? And why? Perfect. Yes, it is ratio. Because when you have 0 megabps, then you have per second, you have no speed at all. Perfect. All right. So a small reminder, I will provide you with the answers later on. Okay, I'm going to share with you a document that includes the answers. Okay. All right, and this is the example that we were all waiting for. Okay, so we have a histogram and box plot. We don't have a normal Q2 plot for this question. We don't care about that. Describe what the box plot tells you. This is the typical way of box plot, right? It's not as we saw in the previous slide. We did it just to explain it easily. So describe briefly what the box plot tells you about the location, the spread, shape, the underlying data, and what does the area of the bar in the histogram represent. Okay, So let's begin with the second. What does the area of the bar in the histogram represent? Do you remember? Okay. That's that's more about A, right? Yeah, okay. So number B is more general. Yes. Okay. Okay. So you're talking about A. Okay. Let's go with A. Right. So the box looks tell you about the location, spread, and shape of the underlying data. So true. The data is considered the -1. Here's -1. This is the median in this case, right? So it's the median. Spread. Yeah. If you include the outliers, it is from -3 to plus something. It will be 0.1, 0.2, I don't know. And the shape, how does this thing look to you? So I think I can zoom in. Yeah. So if you see the length of the queue of the whiskers, these lines here are about the same, I would say. And inside the box, the median, this line here, is about in the middle of the box. So I would say they're pretty normally distributed data. If you say that here the median is a little bit below what was expected, so about not exactly in the middle of the box, but a little bit lower in the middle of the box, you can probably say it's right skewed distributed, right? So again, first see the length of the whiskers, if they're exactly the same or not exactly the same. Okay, about the same. And then have a look at the box. So if the median line is closer to the Q1, this line, it's right skewed distribution. It's positively skewed distribution. If it's in the middle of the box, it's normally distribution. And if it's closer to the top, to this line here, which is the Q3 line, it's a negatively skewed distribution, a left skewed distribution. Does that make sense?
I have a question. Does
Yes.
it mean that when the darker line is going more to the top, so the top it's left and the lower part it's right? How can I imagine that?
Okay, can you repeat your question?
So here the line in the middle, right? If it's
Yeah,
going
about the middle.
more to the top to 0.5, so that means that it's positive or negative distribution. How can I?
If it's closer to this line here, to the Q3
Yes,
line,
yes.
yes, it will be a left skewed distribution.
So the top it's left and down it's right. Okay.
Exactly.
Thank you.
No worries. You probably can see that from here. I mean, these seem like normal distributed data, kind of. They're not so skewed, just like the box, but it's not so skewed. And what does the area of the bar in the histogram represent? This is so it's negatively skewed here. I would say it's, I mean, you can also look at the histogram on the left. Do you think it's negatively skewed? No, I would say it's kind of normally distributed data. Maybe a little bit negative skewed, maybe a little bit. But I don't think that, I don't know, like, this is not a clear example of the negative skewed distribution. Or like here. So not clear example of normal distribution data, but I would say it's pretty normal distributed data. And again, this is the bad thing about graphs, because someone can interpret with different in different ways. Someone would say, hey, it's a negative skewed distribution. Someone would say it's a normal distribution. I would say it's pretty normal here. Okay, any questions with that? Yeah, what about B? So what does the area of a bar, I almost forgot that, of a bar in the histogram represent? So the area of the bar here, let's say this bar or this area or this area. So I think we talked about before, it's the density, so it's the frequency of the X value, right? For example, here we have from -3 to minus, what's that? 2.5. And we see how this bar here represents how frequent this X value is. Make sense? Yeah. Okay, cool. I have one last question. Explain why the following statement is wrong and formulate it in a correct way. So histograms can be used to plot the relative frequency data of ordinal type. Why is it wrong? Does anyone have a good idea? Histograms was for rational data, ratio data. Yeah, yeah, true. Yeah, yeah, yeah. So histograms are indeed for interval or ratio variable. Bar charts are for ordinal types, right? So bars and histograms, they look very close to each other. They look similar, but histograms are interval, ratio variables, and bar charts are for ordinal variables most of the times. Okay, so don't worry if you think that these questions are not so clear or so, obvious right now, the answers. It's they are there to help you for the exam. Okay, so the idea is when you study, you can go through these questions, and just before the exam, they will be clear to you. So it's just some practice, and I hope they become more clear. You can also see in which topics you maybe want to study more or something like that. But again, if you go through again all the material, it will be very easy to respond to them. Now, this is not the schedule of today. I think today we're going to finish with the probability distribution, but definitely we're going to talk about probabilities now. So, are there any questions about what we did so far? About the theory of the data? No? Okay, in that case, let's start with probability. All right. So I think this will be also a big part of your exam. So the probability is how are we sure that the sample value represents the population value? Well, okay, so we talked before that we have a population, we have a sample, and we have to get the results and the conclusion of the sample to the population again. So the probability tells us how sure we are about this generalization of the population. So the probability value between 0 and 1. You cannot have a negative probability, you cannot have higher than 1. And I cannot include I did. Amazing. Okay, so there are 5 important things that we need to remember. Okay, so first, the probability experiment. Okay, this is our example. This is a procedure that produces an outcome that involves randomness. Okay, so for example, when you roll a die, we're going to use this example a lot in this session. So you roll a die, you see the outcome. This is the probability experiment. Okay, the experiment that includes some randomness. Second, more important than before, sample space. So this is the set of all possible outcomes. And we use the letter omega, or omega, I don't know how you call it, omega, yes, to symbolize that. So if you roll a die, what can you have? You can get 1, you can get 2, you can get 3, you can get 4, 5, you can get 1, 2, 3, 4, 5, 6. Yes, I can measure in English. Amazing. So what's my sample space? Omega, and then you equals, and then you have brackets 1, 2, 3, 4, 5, and 6, close brackets. That's it. That's my sample space. And now I can divide the sample space into many different events, let's say. So an event is the collection of many outcomes, right? So we usually use capital letters to symbolize that. So A, B, C, or whatever. So here, an event A would be to throw an even number. So in that case, it would be, again, the same bracket as before, 2, 4, or 6. So my sample space indicates all possible outcomes, and I can group these outcomes into events. Let's say even number thrown or something else. And we also have a simple event. This is, I don't know, one outcome. So again, the same type of brackets, and then 1. I have 2, I have 3 here, whatever. And so it's an event, but it's not a group. So it's a simple event. And then you measure the probability. All right. So how much probable, what are the chances for each event to happen? So you have a value between 0 and 1. So for example, here we have the probability that the event A will happen. So the probability of A, that's what it is. So A here is even number is thrown. So this is the probability, and then a normal parenthesis, and then these brackets here, 2, 4, 6, and then I close with the weird brackets, and then the parentheses, and equals 1 out of 2, right? So it makes sense. We have here total 6 outcomes. Here are the 3 outcomes. So 3 divided by 6, it's 1 divided by 2. Or you can say P05. What's the most important here to remember is that the P, after the P comes the parenthesis that looks like this. But when you try to symbolize an event, you use this type of brackets here. All right. Okay, so let's have an example. Let's say that Alice tosses a fair coin 3 times. So we have to calculate the sample space and the probability measure P for this experiment. So what's the sample space again, omega? It's, let me go back. It's the set of all possible outcomes. So it's omega equals, and then all possible outcomes into these brackets. So if you have a coin, what are the results? You can only have heads and toss, right? Heads and toss, that's how they're called, I think. And you throw it 3 times here. So let's find the sample space omega. So the first possible outcome is that we have all heads. So 3 times heads, heads, heads. The second outcome is heads, heads, toss. Third outcome is heads, toss, heads. And we have toss, heads, 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 toss, 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 heads, toss, 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 heads, and all toss. And then, what's the probability measure for this experiment? So the probability measure here. All of these outcomes have equal probability to happen, right? Because it's a very fair coin. So each event has probability of 1 divided by 8. Why 1 divided by 8? Because it's 1, 2, 3, 4, 5, 6, 7, 8. So all of them have 1 divided by 8 probabilities to happen. Does it make sense? Yes. It's another one in the chat. What does the omega mean? Okay, so the capital omega is the set of all possible outcomes, right? So here, this is the set of all possible outcomes that can happen. Each one of them is symbolized with a smaller omega. I don't think this is a W, I think this is omega, but not the capital one. We can probably give you, yeah, this is the not capital. Capital. It's a good part of being Greek. You have the numbers and the letters. I mean the numbers. We don't have numbers. The letters in our keyboard. Right. So, how do you determine the probability of an event A to happen? And there are 3 different ways And we're going to talk about the first two. So the subjective approach, it's subjective. You can design your approach. But let's first talk about the relative frequency. So the relative frequency, really nice because it's very, very easy. So if we get that, we can, during the exam, I don't know, we can celebrate that. We can be very, very happy because this is an easy question and we want to get all the points from here. So how do we do that? So this is the probability of the event A to happen. How do you find that? Number of items A occurred. So how frequent this event happened, divided by the total number of the times that the procedure was repeated. So let's find an example. In the NBA season 2015-16, Kevin Durant attempted 644 free throws. I have no idea what it is. I hate basketball, but I don't know. He scored 575 of them. What was the probability that Durant hits a free throw? So how do we put these numbers into this formula here? Any ideas? Yeah, it's exactly that. Thanks a lot, Jana. So it's 575 divided by 644. Why? Because we want to find the probability that Durant hits a free throw. I'm sorry. My roommates. Okay, so we want to find the probability that Durant hits a free throw. Okay, so this is the event that we wanted to. So how many times he attempted to do that? 644. So the procedure was repeated 644, and he scored 575. So this is the number of times he scored. So we want to find out the probability that he scores. So 575 divided by 644. Make sense? Any questions here? Cool. Okay, I think we can talk about this after the break. So we can take 7 minutes of break. We can be back at 12:05. So I'll see you then. If you have any questions, I'll be here during the break. Oops. All right, so let's continue and talk about the classical theoretical approach to determine the probability of an event A to happen. Are there any questions so far before we start with the classical approach? Okay, so that means that we can continue. Okay, so before we come to the relative frequency to determine the probability of an event A to happen, now we have the classical theoretical approach. So here we have the number of ways A can occur divided by the total number of different simple events. Now, let's find an example. You take a multiple choice exam with 4 different options. One of them is the correct answer. Let's say that you have no idea what the answer is and you try to guess. So what is the probability of correcting guessing? Here we have 3 different steps. The first one is to find the sample space. The second one is to find the event space, and then put these numbers into the formula. See an example. I'm going to split my screen, make it better. All right. So let's say that we have this multiple choice exam, and this is the population of the Netherlands is 70 million, 8 million, 2 million, or 90 million. So first of all, we have to find the sample space. And this is again all possible outcomes. Okay. So we symbolize it omega, say equal, and then we have all the different events that can happen. All right, so either 1 is correct, either 2 is correct, either 3 is correct, either 4 is correct. And then what we want to try to see is the probabilities of correcting guessing. So since only 1 is the correct answer, the event space, like the only outcome that we can have as a correct answer is only 1 answer. So the event space is, let's say, we call this event A, and we say it's correct answer, right? Oops, I don't have. Let's copy paste that. Let's paste here. Why? It equals 1. I'll put that into brackets. It looks better. Right. So why 1? Because we have only 1 correct answer. There cannot be 2 correct answers. The question here specifies that. So now I'm going to put the event space into the first number here, the number of ways A can occur, because only 1 correct answer can occur, and divided by the total numbers of different simple events. So how many simple events do I have? I have 1 simple event, 2 simple event, 3 simple event, 4 simple events. So the P of alpha will be 1 divided by 4. Does it make sense? Do you think there's something here that's not clear, or it's tricky, or anything? Well, in any case, if you find something, let me know. What's the difference between this one and the previous one? Yeah, so here you calculate the probability based on how many times you try to do something and how many times you achieved. So it's how many times you achieved divided by how many times you tried. But here, you haven't really tried anything, right? So here are the probabilities. Okay, there's so I didn't take the exam. I didn't do many guesses, and I saw how many of them are correct or not. So this has nothing to do with me. This has to do with the exam itself. So it doesn't have to do with my performance. It has to do with the regulations and the rules of the exam. So based on maths, what are the chances that I try to correct guess? And also based on the rules of the exam that I take. So the one has more the individual part as well. So if you're not Kevin Durant, for example, you're not going to have the same probabilities of scoring a free throw. But here, the probabilities of correct guessing should be exactly the same for all the people. Make sense? Perfecto. Okay, so let's try an example question. So executives of a new portal investigate the amount of time each visitor spent on the main page of the portal. Time spent by 25 randomly chosen visitors was measured, and the results of this measure are presented below. Based on the relative frequency, please give an estimate of the probability that a randomly selected visitor will spend more than 30 seconds of the main page of the portal. I'm going to give you 2 minutes on that, and please feel free to spam on the chat your answer. All right, so Joanna says it's 11 over 25, and Brewer says 12 over 25. Oh yeah, 12. Okay, so what we want to see is, let's see the answer. So we want more than 30 seconds, right? So this person has it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So I think that the correct answer is 13 divided by 25. Why 25? Because we have 25 in total chosen visitors, and we have 13 people that achieved more than 30 seconds. Achieved, I mean, it's not an achievement, but okay. They spent more than 30 seconds. So for me, yeah. Oops. Made it nice. So let's see. Why not? The probability here for me, A would be 13, yeah, divided by 25. Also do the math. 0, yes. The number went. Okay, is it clear to everyone? Perfect. All right, so let's dive in more to the probabilities. So first, let's discuss what these symbols are and what they represent. So probability of A, the way we talk about that, is the probability that event A will happen. But now we can also introduce another event. So first case scenario, we have the P of the A, and this sign, and B. So this sign signifies and. So this is the probability that the event A and the event B will happen. So this is the probability that both events will happen. Now, we have the other way around, another symbol, which is the OR symbol. So in this case, we talk about the probability that the event A or the event B will happen. So here we care about both events, and should both of them happen, and here one of them can happen. We care about the probability of one event to happen. And we also have the straight line, which means the given. So here is the probability of the first event, so the event A will happen given that B has already happened, or given that B will happen. And a way to find this probability, the probability of the event A to happen given that B has already happened or will happen, is by this formula, which is the probability that event A and B will happen divided by the probability of the event B to happen. But more on that later. I think the most important part is to familiarize yourself with these symbols. Now, what I try to help myself sometimes as a rule of thumb is that here you have like A, and as a way to remember this symbol, I say that it looks like N, and AND includes N, so it's A and B. This is just me. I don't know if it helps. I'm just trying to help here. I don't understand the last one. Can you repeat it one more time? Oh yeah, A, given the probability that A will happen, given that probability, given that B has already happened. So you can, you can. Oh, that's a really nice way that I just, a nice example, I think. So you know that some people have ADHD, attention deficit hyperactivity disorder. So in most cases, I think in all cases, these people need some drugs, right? You need some medicine to concentrate more. But these medicines let you concentrate more only if you have ADHD. So let's say that you want to come up with a new medicine about ADHD. So you want to see the probability of this medicine helps, given that the event B has happened. And you can say that event B is when you have ADHD. So you want to see the probability that the medicine will help, given that people have ADHD. Maybe it's not a very good example. Does it make more sense? Let's say. So you know that. How can you change the word given? Maybe taking into account that the event B has happened, considering that the event B has happened. I mean, given is like considering as absolutely true. The probability that the medicine will help the patient, given that the patient has ADHD, let's say. Or maybe, you're working in a train company and you want to introduce a new type of subscription, and you say, what's the probabilities of the customers to adopt this new subscription? I don't know, given that this subscription only refers to people who have OV chip card, for example. Yeah, so if B happened, what's the probability of A will happen? Yeah, exactly. Yeah, true. If B happened, what's the probability of, yeah, amazing. Yeah. Yeah. If someone has a basic fit card, that makes real sense. Yeah. Perfect. All right. Yeah, I'm starting to lose my voice, but okay. So let's talk now about Venn diagrams. Right, so we have 6 different scenarios. Let's say that first, we want to find the probabilities that event A will happen. So as you can see here, we care about always the yellow part. So the yellow part here includes A, the circle of A. So, and here it's the circle of B. So here is the probabilities that the event A will happen. Here are the probabilities that the event B will happen. Okay, so we care about all the B, all the A here. Now, we can care about the complement of A. or I'm not quite sure how it is pronounced, A with a tone, I don't know, A power, I don't know. So what in this case, what do we care about? We care about everything that's not A. So the complement of A is all the space here, as you can see, all the space here, except for A. So it's B, and it's all the outside of A and B. And the complement of B is everything that it's outside of B. So you see, it's all the yellow that's outside of the B. It's A and the rest of the space. That's the complement of B. Now, so as we talked before, this is A or B. So now we care about the probabilities that either A or B will happen. And we call this union. So the union of A and the union of B. But when we talk about and, so here it's the probabilities that event A and B happen, we talk about the common part, right? Because we want both A and B to happen. And the only space that we care about is the intersect. That's how it's called. So three main terms here. First is the complement. So the complement is, let's say the complement of A is all the things that have nothing to do with A, that are outside of A. The complement of B are all the things that are outside of the circle of the B. Term number two is the union. So the union refers to when you say A or B. And the intersect is when you care about A and B. So the common space of A and B. Is it clear here? Yep. So, as we said before, union is when you have both, intersect is when you have the common space. Okay, so what happens if the intersection or the intersect of A and B is empty space? It doesn't exist. Like here, we have A on the one side and B on the other side. There is no intersect. There is no connection between these two. So in that case, A and B are disjoint events. Okay. So let's first discuss some rules. Let's discuss the complement. So what is that here? This is the probability that an event A will happen plus the probability that all the events that have nothing to do with A, so the complement of A to happen, equals 1. It makes sense, right? Because we have all the space here. So if we add A and all the other space, what we have everything. So we have 1, because the probability, the highest value of probability is 1. So this is a really nice base, because now we can calculate the probability that the event A will happen, or the probability that the complement of A will happen. So the probability of A, the complement of A will happen is 1. So all the space, 1, minus the probability that A will happen. So in that case, we care about the probabilities of the yellow part. So we say the probabilities of the yellow part equals 1 minus the probability of A. And it's the other way around. So the probabilities of A to happen equals 1, which is all the space, minus the probabilities of the complement of A, of the yellow part. let's give you an example. Let's say that we roll a dice. So we can have 1, 2, 3, 4, 5, or 6. The third dice. So my A here, the event that I care about is that I have a 6 as the outcome. And the complement of A is that anything that doesn't have to do with A. So it's 1, 2, 3, 4, 5. All the events that are not A. That's the complement of A. So if, okay, each outcome has probabilities of 1 divided by 6, right? Because I have 6 different outcomes. So each outcome has 1 divided by 6 probabilities. And if I add all of them, I have 1, right? You have 1 divided by 6 plus 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 1 divided by 6. I get 6 divided by 6, so it's 1. So what's the probabilities of complement A to happen? It's 1 minus the probabilities of A to happen. So the probabilities of this thing to happen is 1 minus 1 divided by 6, because this has probabilities divided, has the probability 1 divided by 6 to happen. And the probabilities, and the probability for A to happen equals 1 minus the probability of this to happen, of the complement of A to happen. Make sense? Okay, perfect. Change the slide. I changed. All right, so let's have a question. Given, okay, I mean, we have 2 events, that's what given here means, 2 entirely disjoint events, A and B, okay? And both of them have a probabilities higher than 0 to happen. What's the probability that both A and B to occur? So what's the probability of A and B to occur? So we have ones, we have, yeah, so it's at 1, so it's at C. What else? C, okay. Okay, let me give you a real life situation. Let's say that, okay, how many people are we here? We're 70. We're 70 people. Okay, so I draw someone of you entirely randomly. I select one of you entirely randomly. And let's say we have 2 disjoint events. Okay, so that person is either a male or a female. Okay, this is what disjoint events are. So you can either have A or you can either have B. So you can either be male or you can either be female. So if I do that, if I select one of you, what's the probabilities that this person that I choose is both male and female? Does this change your answer? Okay. Thought about. Yeah, I think it's 0 too. And I also agree, gender is a weird example. True. But the thing is that the events are totally disjoint. So you can either have A or you can either have B. So if you want to measure what's the probability of both of them to happen, it's 0. There's no way that you can have both of them, because you either have A or you either have B. Because the question asks what's the probability that both A and B occur. It is a tricky one, I know. Yeah, I know, it's quite tricky. So I don't know, let's say that we divide our, we're 17 here people, 17 people here. Let's say we divide our sample into young people and old people. So you're going to not be both old and young person, right? So you can either be A, young, or B, old. So if I take one of you, if I select one of you randomly, what's the probability of this person being both old and young? It's 0. There's no way that this can happen. Perfect. All right. So let's talk about more rules about probabilities. So first, let's talk about addition rule. Okay, so the addition rule is when we ask the probability of A or B. So the probability of A or B. So it's not like we did before, because before in the example question, we asked and, right? A and B. So now we asked A or B. So the addition rule changes if the events are joint or disjoint. Again, the disjoint are, they don't have any intersection. So it's A and B, they don't collide to each other. So if the event is joint, then we use this beautiful formula here. So let's try to see if we make it more easy. So here, we want to see the probability of A or B to happen. So we really care about the red space and the light green space. We don't care about the dark green because the dark green is A and B. Prob, I'm not sure which, what are you referring to now? In this here, the symbol? or is it in previous slide? The last question. Here, the given. Yeah, given to it. Yeah. No, it's like if I give you two events. Okay, like assuming that two entirely events A and let's assume that two entirely disjoint events exist, A and B, because the probability here it's clear, it's A and B. Okay, it has nothing to do with this given. No, nothing to do with that. Cool. Okay, so additional rule. Let's talk about the joint again. So we care about A or B. So we care about the light red and the light green. We don't care about the dark green because the dark green area is A and B. So what do we say? We say it's the probability that A will happen. So all A, including this beautiful thing here, and the probability of B happen. So again, all of B, including this beautiful here, this beautiful thing here, minus the probability of this beautiful thing. So it's the probability of A plus the probability of B minus the probability of A and B. And with these joint events, we don't have this one. We don't have the probability of A and B because we don't have A and B. We don't have the dark green area. So in this case, it's the probability of A plus the probability of B. So if I come back to the example that I said before, let's say that we are 17 again, people here. We divide our sample into young and old people. Let's say that this is balanced. So we have, let's say we are 16. Okay, so we have 9 people, 8 people that are young and 8 people that are old. And if I select one of you and I say, what's the probability of being young or old? In this case, we have these joint events because you cannot be both old and young. So what's the probability of being young? It's 8 divided by 16, so it's 0.5. And again, being old has exactly the same probability because it's 8 divided by 16. Again, it's 0.5. So in that case, the probability of selecting a young or an old person would be 0.5 plus 0.51. So that makes sense because I will definitely select either a young or an old person. Okay, makes sense here? The addition rule is clear? Cool. So now let's talk about another question. So the probability of a union, there's something that's not? Of the joint. Okay. Yes. Okay. So here one. Yeah. That part. Okay. Cool. So let's find two joint events. Okay. So let's say that event A is that you're rich, and event B is that you are male. So there are some rich people, there are some males, and there are some rich males, right? So we have both of these events happen here in the middle. So again, we have the red part is the rich people, the B, the light green part is the males, and the dark green is both reads and males. So now we care about the probabilities of either being reads or being male. So we care about the red part and we care about the light green part. We don't care about reads male people. Very weird thing to say, but okay. Okay, perfect. So it's the probability of being reads plus the probability of being male minus the probability of being reads and male. We don't care about reads males. All right, cool. Exam question. What's the probability of a union of two events is always less or equal to the sum of the probabilities of these two events. Let me go back a few slides. So we care now about the union, right? You see? So all of them. So the probability of a union of two events is always less or equal to the sum of the probabilities of these two events. So let's say that, okay, here. So we have again reads, and we also have males. We have reads males here. So we care, oh, where am I? We care about the probability of being reads, reads and males or male to be less or equal to the sum of the probabilities of these two events. So these two events is reads and male. Sum or the union. Yeah, here they refer to the sum of the probabilities of the two events. Okay, so let's say if I go to that example here. So here we can see that, let's have this. I think that the circles are equal. So let's say that the probability of A to happen is 0.5, right? So the probability of being reads is 0.5. And the probabilities of being male is also 0.5. Okay. So what's the sum of it? 0.5 plus 0.5. It's 1, right? And now it says, the question says, okay, if I add the probabilities of A to happen, plus the probabilities of B to happen, plus the probabilities of this beautiful thing to happen, must be equal or less to the probabilities of 1. Does it make sense? I mean, there's the true. There's the mathematical way, but I think the graphical way is easier to understand. So the mathematical way is that, okay, I have since there are joint events, right? They're joint. So what did I say for joint events? The probability of A or B, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, just like I did here. So the probabilities of A, the probability of B minus the intersection. So this beautiful bastard here is non-negative, it's a positive value. So in all cases, I have the probabilities of A or B minus or equal to A and B. The non-negative disclaimer, yeah, the non-negative means that it's a positive value. So what's the probability of A and B to happen? It's a positive value. It might be 0.2, it might be 0.1, it might be 0.9, for example, but it's definitely a positive value. So it's like, okay, let's imagine that we don't talk about probabilities now. Let's talk about something else. Let's say 5 plus 3 equals 8, right? Minus 2, let's say this is 2, equals 6. So this equals 6, but this here equals 5 plus 3, because we said 5 plus 3 equals 8. So you see, always this formula will be equal or less than this formula. It is less than or equal. It can also be equal. Ah, nice question. When it can be equal? When these two formulas can be equal? Yes. If the intersection is an empty set, yes. True. If there are disjoint events. Amazing. True. If there are disjoint events, then it's equal. If it's a disjoint, then they are less. Perfect. And also a tricky one, because here we talk about the union of two events. Let's go back. So the union of two events, even though there's no, even though A and B can be totally separate here, we still can talk about union. We don't talk about intersect, so the space that one lays upon other. We talk about A or B. So this is union. This is union also, because we have either A or B. They don't need to be like that when it comes to union. Amazing. All right. Let's do another exercise. Okay, let's first talk about this. Are there any questions here? I still don't really understand why it is correct. Okay. The probability of a union of two events. Okay, so what's the probability of a union of two events to happen? So the probability of two events is this. We talk about union, so it's either A or either B. Okay, we don't talk about intersect, we talk about union. So either A or B. So in these cases here, we have the probability of A plus the probability of B. If you sum this, then you get the probabilities of A or B. So it's equal here, right? So the union, this is the union. A or B is a union, equals the sum of probability A plus the probability of B. But when it comes to joint events, we have the probabilities of A plus the probabilities of B minus their intersect. This beautiful bastard here. So the union of A or B, actually the union of A and B, that's how it's called, or the probabilities of A or B is less than this sum. Why? Because we subtract a number here. Is it now more clear? Yes, intersection is the overlapping value in both A. Yeah, we don't need it. No, when it talks about with, yeah. Yes, exactly. So when we talk about union, we care about A or B? Not A and B. Perfecto. I don't know why I talk Spanish, but okay. Okay, suppose you roll a die once. What's the probability to throw an even number or 3? So let's go through all the steps together. First, the sample space. Omega equals 1, 2, 3, 4, 5, 6. Okay, we have a die. We can get one of these 6 events. So now the question asks us about the probabilities that you throw an even number or 3. So they asked us about 2 different events. The event number A is throwing an even number. So what does even number means? 2, 4, 6. So 3 possible outcomes. 3 divided by 6, which are here, the number of events in my sample space. So it's 1 divided by 2, I mean 0.5. And the event B is that we throw a 3, right? So we throw a 3. So here, the probability of B equals 1, because I only have one number, divided by 6. Divided by 6, because I have 6 different numbers here. Okay, and now we have to combine these 2 events. How do we combine them? They ask us about OR, right? So first, let's see if they are joined or disjoint. Now, if you throw an even number, you throw 2, 4, 6. If you throw a number 3, it's not included here. So A and B are disjoint. You cannot throw 2, 4, 6, and 3 at the same time. So they're totally disjoint. And since they're disjoint, I go to this beautiful rule that says that P of A or B, because this is what I have been asked, even number or 3. So the probability of A or B equals the probability of A. I have it, 1 divided by 2, plus the probability of the event B, which is 1 divided by 6, equals 2 divided by 3. So this is 2 divided by 3, almost 66%. Oh, that's nice. So step number 1, define the sample space. Step number B, define your first event, find the probability of that, define your second event, find the probability of that, see if these events are disjoint or joint, and then use the formula. You have it. You have the probabilities that you throw an even number or 3. Is it clear? Yes. Okay. I think we're almost over time. So you can practice with this recap exercise at home. I mean, you're at home, I guess. But okay. I think we can stop here, and we will continue tomorrow. So I guess you're free to go. I hope you enjoy your Saturday morning. I'll see you tomorrow. For some people, not for some people, I would really, really, really appreciate if you guys stay like 2 minutes more and just tell me something in the chat or unmute yourself. Tell me, how did you find the session? How do you feel? Was it helpful or not? What would you like to see? Can we get the recording from today? I think you have to contact someone else about that. I'm not responsible for that. I don't have the recordings myself. Yes, tomorrow is at 10. So I cannot really distribute the recordings because I don't even have them. Okay, let me see who is in the group chat. Okay, there's one girl that's called Madeleine, I think. She's responsible for the recordings, so you can, I think, so you can ask there or send her a text or whatever. Any feedback on how was the session? Very helpful. That's good. Good to hear.